astronomers were prepared for a spectacular display when their telescopes finally reacquired ThreeI Atlas on November 5, 2025. Based on everything known about comet behavior, they expected a brilliant scene: a long, glowing tail and an expanding cloud of dust and gas. The natural aftermath of a comet passing its closest point to the Sun. That moment, known as perihelion, is when comets almost always become most active. Instead, what appeared on the screens stunned everyone in the control room. There was no tail, no visible coma, no surrounding dust cloud at all. Every instrument showed only a single, compact point of light, a result that violated the most basic expectations of post-perihelion comet activity. This unexpected silence pushed scientists toward an unsettling conclusion. Something significant must have occurred during the 3 weeks when the comet was hidden behind the Sun, completely out of reach of Earth-based observation. What kind of event could shut down a comet precisely when it should have been at its brightest? To understand the mystery, researchers first looked at the object's extreme speed. ThreeI Atlas entered the inner solar system traveling between Earth and Jupiter at roughly 129,742 miles per hour, making it the fastest interstellar object ever recorded. Before perihelion, astronomers observed its activity increase week by week. A dust coma steadily expanded around the nucleus. Gas emissions intensified, and early images revealed a young tail beginning to form behind it. By August, the object produced something even stranger: an anti-tail pointing toward the Sun, created by slow-moving ice grains. Then, in early October, the comet's color shifted toward an unusually deep blue, a change that puzzled observers because typical comets always appear redder than sunlight. All signs pointed toward an approaching peak in activity. However, the comet reached perihelion on October 29th while completely hidden behind the Sun, forcing every ground-based telescope to lose sight of it for nearly 3 weeks. When it reappeared on November 5th, the change was absolute. The once active object now looked like a silent, inert point of light, showing no visible energy or ongoing activity. Brightness measurements since then have revealed a steady decline, fading from magnitude 16 to magnitude 20 by February 2026, with predictions indicating it will become untrackable by June. This leaves scientists with only a short window of about 4 months to extract as much information as possible before this ancient visitor vanishes forever. At the center of this chapter lies the eerie quiet of ThreeI Atlas, because according to well-established physics, a comet should become more active after passing perihelion, not less. This rule has been confirmed repeatedly through decades of solar system observations. When a comet approaches the Sun, intense heat strikes its surface and gradually penetrates deeper layers. That heat does not vanish immediately once the comet moves away. Instead, thermal energy continues to travel inward through dust, rock, and ice, a process known as thermal conduction. As a result, subsurface ice keeps sublimating long after the comet has passed its closest point to the Sun. This delayed heating is why the post-perihelion phase is usually the brightest and most dramatic period in a comet's life, with the interior remaining warm even as the surface begins to cool. Because of this, astronomers fully expected ThreeI Atlas to erupt with activity when it emerged from behind the Sun. The final observations before the blackout supported this expectation. Its brightness was steadily increasing. The dust coma was expanding, and deeper layers appeared to be breaking apart. Gas emissions were growing stronger, indicating that the interior had reached temperatures capable of releasing more volatile compounds. The developing tail was already stretching outward, and its early structure suggested it would grow significantly larger after perihelion. Every piece of available data pointed toward an intense and dramatic phase ahead. That is why the silence that followed came as such a shock when the blackout began on October 15th. For 3 weeks, as the comet slipped behind the Sun, researchers revisited the last measurements repeatedly, trying to anticipate how powerful the post-perihelion outburst might be. Many imagined a brilliant tail extending millions of miles, accompanied by strong dust and gas activity. Instead, on November 5th, the comet returned as little more than a compact dot of light. There were no jets, no dust, and no visible signs of sublimation near the nucleus. Even the faint activity detected earlier had vanished entirely, leaving behind an object that resembled a quiet asteroid rather than a heat-laden comet. This transformation deepened the mystery because no existing comet model can explain a complete shutdown at that stage. A comet cannot cool instantaneously after being exposed to extreme heat, and its inner layers should have continued warming during the very period it was out of sight. Scientists compared the situation to a pot of water reaching a boil and then instantly freezing the moment the stove is turned off, a reaction that has no physical basis, especially for an object rich in frozen material. Faced with behavior that defied conventional physics, astronomers were forced to consider explanations far beyond what they normally expect from a natural comet. One proposed explanation suggested that the comet may have broken apart during the blackout, leaving behind fragments too small to produce noticeable activity. Another idea argued that intense heating near the sun could have caused the surface to harden into a thick crust, sealing in any remaining gases and preventing them from escaping. A third possibility claimed that the comet had simply used up all of its volatile ice, leaving nothing behind to drive further outgassing. Each of these scenarios points to a different kind of extreme event, and each one reshapes how scientists think about interstellar objects. The real difficulty lies in determining which explanation best matches the evidence, because all three leave unresolved questions. As new observations arrive, researchers hope to narrow the options, but each additional detail only deepens the tension surrounding the mystery that began during the blackout. This brings the investigation back to its core question: did ThreeI Atlas fragment, seal itself shut, or lose all of its volatiles during the brief period when no one on Earth could observe it? The next phase of analysis begins with the three main explanations scientists are using to interpret the sudden silence of ThreeI Atlas, a silence that standard comet models fail to explain. The first idea centers on fragmentation, proposing that the nucleus may have shattered under the intense thermal stress it experienced near the sun. If this occurred during the blackout, the resulting pieces would have been too small to sustain a visible tail or a bright coma. Fragmentation is a well-documented phenomenon in comet science, and there are real examples that support this possibility. In 2020, Comet C/2019 4 Atlas completely broke apart into dozens of small fragments, leaving behind only a faint cloud of debris. Another case involves the interstellar comet Borisov, which lost roughly 0.1% of its total mass in a single event during its approach to the sun. These examples show that thermal stress can cause comets to fail suddenly and without warning. A similar structural collapse could have affected ThreeI Atlas. If the nucleus did break apart, then the quiet point of light observed after the blackout would make sense, as each fragment would be too small to produce strong outgassing. Many astronomers consider this explanation plausible. However, they also point out a troubling detail. Observations before the blackout did not show a sudden drop in brightness, which often appears shortly before a comet breaks apart. This absence introduces uncertainty, meaning fragmentation alone does not fully resolve the mystery. The second explanation focuses on complete volatile depletion, suggesting that all sublimable ice inside the comet may have been consumed by the extreme heat at perihelion. Volatile materials such as carbon dioxide, water, and carbon monoxide normally drive the gas release that forms comas and tails. If these substances were entirely exhausted, nothing would remain to generate visible activity. In this scenario, the comet would have become an inert body made mostly of rock and dust, incapable of releasing gas even when heated. Some scientists find this idea reasonable because the comet showed strong activity in the weeks leading up to perihelion, implying that near-surface ice may have been rapidly depleted. However, this explanation creates another problem. Deeper layers of ice are usually protected and continue to sublimate due to thermal conduction long after the surface cools. For total depletion to occur, the comet would have had to burn through every reservoir of ice, including its deepest stores, during a blackout that lasted only 3 weeks. This seems unlikely, making the depletion theory incomplete. As a result, scientists remain uncertain that volatile exhaustion alone can explain the complete silence of ThreeI Atlas. The third explanation is known as mantling. This theory proposes that radiation-processed organic material on the surface melted and fused during perihelion, forming a hardened crust similar to cosmic asphalt. Such a layer would trap any remaining volatile material beneath it, preventing gases from escaping even if the interior continued to heat up. Mantling is a known process in aging comets, and several extinct comets within the solar system show sealed surfaces that conceal deeper ice layers. If ThreeI Atlas formed such a crust during perihelion, it would appear completely inactive from the outside despite still containing frozen material internally. Among the three ideas, the mantling hypothesis explains the sudden shutdown more smoothly than the others. A sealed crust can form quickly under extreme heating, and the blackout period provided enough time for this process to occur. This explanation also fits the lack of a dramatic brightness collapse before the blackout, since mantling does not always alter a comet's light curve in advance. Still, mantling leaves unanswered questions, particularly the lack of direct evidence for surface cracks or variations that would confirm the presence of a hardened shell. To help resolve these uncertainties, the Hubble Space Telescope conducted a new observation campaign just 3 days before the point described in this timeline. The results of that effort are expected to clarify whether major fragmentation occurred and will help guide researchers toward most likely explanation in the weeks ahead. Yet the mystery still hinges on details that remain only partially understood. This brings the chapter to its central question: which of these explanations truly fits the impossible silence we are witnessing now? One of the most startling aspects of this investigation lies in the chemistry of ThreeI Atlas. Measurements collected before perihelion revealed a composition unlike anything ever recorded in a comet. The data showed that 87% of its gas output came from carbon dioxide, while only 4% was water vapor. This result stunned researchers, because comets are normally dominated by water ice, with smaller contributions from carbon dioxide and carbon monoxide. The imbalance seen in ThreeI Atlas went far beyond a minor variation and produced a ratio that Saturday, June 1st standard deviations outside normal comet values. In scientific terms, a deviation that extreme signals that something highly unusual shaped the comet's chemistry. The production rates deepen the mystery even further. The comet released about 129 kilograms of carbon dioxide every second, compared to only 6.6 kilograms of water vapor. These numbers directly contradicted every standard formation model used to explain how comets develop in young planetary systems. Those models predict that 70 to 80% of a comet's volatile content should be water ice, since water condenses easily in cold protoplanetary regions. Carbon dioxide usually plays a secondary role because it freezes at lower temperatures and is expected to exist in much smaller amounts. Nothing in these models explains how a comet could end up dominated by carbon dioxide while containing so little water. This contradiction forced scientists to search for explanations that do not rely on ordinary processes familiar from our own solar system. The lack of visible activity pushed researchers to consider mechanisms that obey known physics but remain hidden from direct observation. One idea proposed that the comet could be releasing hydrogen gas, which is invisible from Earth because the ultraviolet wavelengths needed to detect it are absorbed by the atmosphere. Hydrogen outgassing could generate real thrust without producing any visible structures, making this explanation plausible. Another possibility suggested that heat stored deep inside the comet during perihelion might still be driving sublimation from sealed pockets beneath the surface. In that case, gas could escape through fractures too small to form visible jets, yet strong enough to affect the motion of the nucleus. A third idea argued that the thrust influencing ThreeI Atlas today may have been generated before perihelion, with the resulting change in velocity simply continuing along its path even after the jets shut down. This scenario implies the comet received a strong impulse during the blackout and has been carrying that momentum outward ever since. All three explanations rely on hidden forces, and each attempts to fit the data without violating established physical laws. However, the comet's trajectory makes the puzzle even more difficult. Its orbital eccentricity was measured at 6.14, the most extreme hyperbolic path ever recorded for an interstellar object. Such a value means ThreeI Atlas is not gravitationally bound to the Sun in any way. and no interaction within the solar system could have accelerated it to this speed. It arrived fast and is leaving even faster, with an acceleration that scientists can measure but not directly observe. This unusual motion makes the coming months especially critical, because the final opportunity to test these theories will occur in March 2026 during the Jupiter flyby. The comet will pass within 0.36 astronomical units of Jupiter, close enough for the planet's tidal forces to stress any sealed crust or fragile internal structure. If ThreeI Atlas formed a mantle during perihelion, Jupiter's gravity could crack the surface and allow trapped gas to escape again. A sudden return of activity would support the mantling. Explanation: if nothing changes during or after the flyby, the depletion theory becomes the strongest candidate, since a comet without volatiles has nothing left to release. But if the nucleus fractured during the blackout and the object is actually a cluster of fragments, Jupiter's gravity should pull those pieces farther apart. In that case, telescopes would detect multiple sources instead of one, confirming fragmentation within days. The flyby represents the last experimental test before the comet fades beyond detection. And every possible outcome will reshape how scientists understand interstellar visitors. Each theory will either stand or collapse based on what Jupiter reveals. As ThreeI Atlas enters the planet's gravitational reach, the chapter reaches its final question. Jupiter will decide which explanation survives and which ones fall apart. But what will the sky reveal when that moment arrives? ThreeI Atlas is fading by roughly 1/10 of a magnitude each week, and soon its light will sink below the detection limits of nearly every telescope on Earth. Only the Vera Rubin Observatory may be able to track its path for a short time longer, and even that instrument will lose sight of it by June as the object slips back into darkness. Scientists understand what is at stake. This comet carries chemistry shaped inside a stellar system that died billions of years ago, and every observation could be the last chance to study material older than the Sun itself. The next 4 months are the final window to uncover answers before the mystery becomes unreachable forever. What happens during the Jupiter flyby will determine which theory holds. And once ThreeI Atlas disappears, no new data will ever come again. So the question now passes to you. What do you think caused the tail to vanish? Fragmentation, total depletion, or catastrophic crust formation?